What's up, guys? Welcome to the fifth review preview session for ENGI 1331. I appreciate you guys joining me on this Sunday. Today's session is going to be pretty quick. We're not going to do too much because next week you guys have just nested for loops. Since we've already done while loops and introduced for loops, we're just going to do a couple of examples of how to utilize nested for loops, and hopefully it'll kind of inspire you guys on how to do the next in May. So this first example is I titled it Summing Particular Values in a Matrix. So in this case, what I did was I summed only values that are located in both an odd row and an odd column. What I did was I used a double for loop to go through the matrix and use this line right here to test if both the column and the row was odd, and then summed that value to whatever I had originally. And so it was something along the lines of this: even or odd row, odd column, odd row, odd column, odd row, odd column, odd row, even column. Obviously the even rows were all even. And so we're going to go ahead and work through one of these together. So I'm going to copy this line down. We'll need this line again. But now instead, let's only sum values that are located in both an even row and an even column. Okay, so it'll look something along the lines of this: even row, even column. So only summing 4 values. Okay, so how are we going to do this? Well, I started with a matrix M. I'll run this to get all these out of the way. I started with a matrix M, and I want to sum this value, this value, this value, and this value, corresponding to even rows, even columns. So since we've been learning double for loops in class, and we've kind of seen something like this in class, I'm going to assume we're going to use a double for loop here. So to start our for loop, you use the keyword for. Let's say some counter variable I goes 1 through the number of rows of M. And now this for loop goes a different counter variable 1 through the columns of M. Okay. So what we did is we printed out 34, 73, 25, 39, and so on. 34, then 73, then 25, then 39, then 45. And then after 45, we jumped to 42. So it looks like we went for the first row, went column to column, and then at the end, jumped to the next row. And that's exactly what we did. Because I was ran through 1 through rows, and J was ran through 1 through columns. So when we jump in, we hit this for loop here. I is defined as 1. Then we hit this interior for loop here. J is defined as 1. We print out M and IJ. We hit this end right here. We bounce back up into the innermost for loop because this end right here is connected to here. J now becomes 2. So now we move to the second column, print out the next value we print out would be the first row, second column. Hit this end again, move up, third column, fourth column, all the way till we get to the fifth column. After that, J hits its final value of C. We hit this end, we finish. We don't go back up because J has now hit the last value. We hit this end, bounce back up, I becomes 2. So now we're on the second row. Now when we hit this 4 again, it's not like we're repeating it, right? We ended it, hit this end, bounce back up here. So now when we hit this 4 again, we redefine J to be 1 again, and it moves through C. So we repeat that process again. We repeat this process for how many times we repeat this process. So now I would become 3, which is the last row, so we do it again. We hit this end, I was its last value R, so we move on. That's what happened here. So we don't want to print it, right? We want to add only values that are located in an even row and an even column. So to do this, we're going to use an if statement because we're only summing values if they're located in an even row and an even column. We're going to have 2 conditions, the even row and the even column. So how do we figure out if our row is even? Whatever row we're on, while inside of this for loop pertains to I, right? Because I moves 1 through the number of rows, so it's going to be our row index. And our column index would be j. So we know that this one is going to have something to do with j, and this one's going to have something to do with I. So in this one, we're testing if I is even. To do this, we're going to use the rem function. And so I have it written down here. Okay. So the remainder, the variable remainder, becomes rem of divisor and dividend. This function rem divides divisor by dividend. If there is a remainder, it will be stored in the variable remainder. If not remainder, this variable will store 0. So in other words, if the divisor is a multiple of a dividend, remainder, the variable, will store 0. Okay, so knowing this, if I is even, it's going to be a multiple of 2, right? So that means our remainder should be 0. Rem of I divided by 2, that equals 0. That means we are an even row. We do the same thing for j. And what do? Let's define some variable total. Becomes itself plus m at ij, since we have confirmed that I and j are both even indices. We also need to make sure that tot is first defined as 0. So what we're doing here is we can change these conditions here and sum up different aspects of this matrix, or we could do something totally different. We don't have to take the sum, we could take the square root, we could change the values in it, just depending on what these conditions are right here. So what I did with this example is I showed you guys how we can move through a matrix element by element and do different things with those values. So my second example is, the idea of this example is we're going to have a series of second degree polynomials. So this example, 4 of them, there could be many more. And we want to plot all of those polynomials. And we want to see all of them just shown out to us in a graph, on the same graph. So to accomplish this, what we're going to do is we're going to use the randi function to create a matrix coef with its values being a maximum value of 100, 20 rows by 3 columns. And what we're going to do is we're going to take the size of that matrix. We define x as the domain of which we want to plot these second degree polynomials on. And so we run a for loop of 1 through r, just defining the coefficients a, b, and c each time this for loop runs. We define another for loop j to be 1 through the length of x. And so y at ij, the row and the column, becomes the value of this general polynomial with coefficients a, b, and c, corresponding to different columns from within this matrix. We're going to go ahead and try this on our own. Okay, so to begin, let's define our housekeeping commands. And let's define a matrix of coefficients that has a maximum value of, say, 100. And we want to have, let's say, 20 different polynomials, second degree polynomials, of course. So that means that our columns should only be 3, which corresponding to 3 coefficients. So again, let's go ahead and write down this general equation. Ax squared plus bx plus c. We're going to have 20 different kinds of polynomials. Let's say, better. So we want to have a general, this is a general equation of a second degree polynomial. We're going to make 20 different sets of them. So meaning 20 different A's, 20 different B's, 20 different C's. And so the total number of A's, total number of B's, and total number of C's should equal 60. So let's define a matrix coef to be a matrix of random integers, 20 being the, or 100 being the max number, 20 rows by 3 columns. So this column corresponds to A, this column corresponds to B, this column corresponds to C. Each row corresponds to a different polynomial, second degree polynomial that's being graphed. So to begin this, we make a for loop. Well, before that, we take the size of this matrix. Well, we know it's going to be 20 by 3, but we can go ahead and say size of close. We'll make a for loop running from I, the counter variable, from 1 to, what do you guys think? Let's go with R. And so what the purpose of this for loop is, we're now varying which row we're on during every iteration of that for loop, meaning we're varying which set of coefficients we want to use, meaning we're changing from polynomial to polynomial. So let's go ahead and define them. A becomes coefs at row I, 1. B becomes coefs at I, 2. C becomes coefs at I, 3. So now we define another for loop. Let's say J equals 1 through, excuse me, we forgot to define what X was. We forgot to define what the domain of which we want our polynomials plotted on. So let's go from negative 100 to 100. And these brackets aren't necessary, that's fine. So 1 through the length of X. And you'll see why later, why we didn't define X to be, or this counter variable to instead be X equals negative 100 to 100. You'll see why we instead used a different variable for this for loop instead of just defining X in a second. So now we say Y at row I, J equals our general equation. A times X at J squared plus B times X at J plus C. We end this, we end this. So what we're doing here is first we enter this for loop, define our counter variable I from 1 to R. During the first iteration of this for loop, I takes a value of 1. We define our coefficients. A becomes coefs at I, comma 1, B becomes coefs at I, comma 2, and C becomes coefs at I, comma 3. So during the first iteration, use row 1 being I, and column 1 being A. So during the first iteration, our A is 71, our B is 27, and our C is 33. Hit this for loop. We say J is 1 through the length of X. So the 1 through the number of elements in X. Okay? We say Y at IJ, at row I, column J, so at row 1, column 1, in this case, in the first case, becomes A times X at J squared plus B at X times X at J plus C. So this is just the general equation. We're taking X at 1, storing it in 1, 1, corresponding to the first row corresponding to the first set of coefficients, and the first column corresponding to X at 1. And so as we move through this for loop right here, like I said, it's going to run to completions. It's going to run from X all the way to the length of X, getting the Y values for the first set of coefficients because we haven't reran this for loop yet. So once this is done, getting all the values of Y for every different X in this interval, We hit this end. We bounce back up. I becomes 2 now, meaning we're using A, B, and C are defined at row 2 of coefs, still a constant value of column 1, column 2, and column 3. So that means we used a second set of coefficients, A, B, C. When we jump into this for loop again, roll x all the way through the domain of negative 100 to 100. Get the y values corresponding to those x values, hit this end, bounce back up, I is now 3. We use now the third set of coefficients, and so on. And so what it's going to look like is something along these lines, just a bunch of different polynomials graphed from negative 100 to 100. Well, not graphed yet, because all we did was store them in y. So if we run this, every different column in this matrix corresponds to a different value of x. So this is the y value of the first polynomial at a value of x equals 1. Or negative 100, excuse me, because our first value was negative 100. This is negative 99, negative 98, 97, 96. And every row corresponds to a different polynomial, meaning a different set of coefficients. So now, to graph this, all we got to do is say, let's define a figure window. And say we're going to hold on that figure window, meaning we're just going to plot all in that figure window. T becomes 1 through I guess we have to take the well, actually we can just say 1 through r, because that's how many different polynomials we have. It was the rows of coefficients. We say plot x, the range negative, or the domain negative 100 to 100, y at p, all columns. Because now what we're doing is we're plotting, the reason we said all columns is because now we're plotting, again, all the y values that correspond to all the different x values. During every iteration of this for loop, we use a different row of y, meaning a different set of coefficients, meaning a different polynomial. We run this. That's what we get. And so we can do this, let's say, we put a range of negative 100 to 100. And we say we want 100 rows. Look at that. So that's really all I have for you guys today. I just wanted to give you guys a couple examples, a couple things for me to kind of talk through for you guys to hopefully you understand working through for loops a little better. Hopefully this gives you a good idea of how to do maybe MA5 or 4. I appreciate you guys coming out again, and I will see you guys next time.